Hello and welcome back. In these new sets of videos, we are going to look at linear transformations, transformations for neural networks. Now, this is a step forward. So we are going to build on the algebra that we learned in chapter 5, where we looked at what is a basis set. We looked at uh, we looked at how to expand vectors. We looked at how to find orthogonal vectors and so on and so forth. So this is sort of building on what we learned in the previous couple of videos. The first point that we need to understand is transformation. So what is transformation? Transformation, as the name suggests, we are sort of changing something. That's what the name implies, and that is exactly what it is. A transformation it is some kind of a rule that takes in some input from a particular set and outputs something in another set. So let's say if our set is x is equal to x of I, then for each x of I, this rule would output something in the new set. Let's say that is y, and we'll have a corresponding y of I. So the rule number one is there is uh, uh, there are such inputs, uh, and this is called as domain, and then there are such outputs which is called as range. And then there is, so this is the first rule of transformation, this is the second rule of transformation, and then the third rule is that uh, uh, we have uh, we have some so that's the rules. And so to write the rule, we can write it as, let's say, y of I is equal to a x of I. So for each any value of x of I, we apply the rule to get the value of y of I. And that's sort of the general uh, thinking around transformations. Now let's look at some examples. The very first example for the transformations to be linear is the following. So we what we are interested in is linear transformation. Now, how do we know it's a linear transformation? So it has two simple rules. The first one is, let me denote by a different color. Let's say this one. First one is additivity. What this means is, let's say we have two vectors x1 and x2. If we add them and then apply some rule A to this sum of these two vectors, it is the same thing as applying the rule A to each of these vectors first and then adding them together. So that's rule number one. So what this says is that uh, the rule uh, that is there, it doesn't distort how things add up. So after addition, things remain consistent. Either we do this way or this way. The second is scaling. And in scaling, what we are saying is that if we have a vector x, if I scale it by multiplying it with some value, scalar value a or some number, and then apply the transformation rule A, that is the same thing as applying the transformation rule A to the vector x first, and then multiplying that with the scalar value A. So what this is saying is that if we double an input, then the output also doubles in the same direction. So to sort of get a feel for how this looks visually, let's look at some of the plots in Desmos. And I'll put a link to each of these in the description below. Let's say we have a vector, so I'm going to put this off. So we have vector, this one x1, which is along the x-axis. We have vector y, x2 along the y-axis. Now if we sum them and add them, we get this green vector, which is 2 2. So that's what we know. Now what we can do is we multiply it with the scalar value 2 first to get the vector a1. So that's scaled, as you can see. The earlier red arrow was only up to 1, now it's up to 2. Likewise, we scale the vector x2, that again goes up, blue arrow that goes up to 2. And now we add these a1 and a2 to get a resultant vector, which is this one, which again overlaps with the green dotted vector that we had earlier. So this is sort of the visual visual about how that rule holds that we just looked at, where we said that if we add x1 x2 first and then apply the rule, it is the same thing as applying the rule individually to x1 and x2 and then adding them later. The next example is again the same thing, except that here we see that the vectors are at an angle to each other, sort of are trying to form a parallelogram. If we now again look at the x1, let me uh, hide those. We have the vector x1, which is here along x. We have vector x2, which here is along y, and then we have the vector x1 plus x2, which is right here, and then we scaled it by 2. So if we simply have the x1 x2, it would look like this, and that is fine, except that we are also scaling it in this case. So we sum them, scale them, so that's the same. uh, so that is the same thing as first scaling each vector. So I scale the x1 as a1, scale the x2 as a2 by multiplying by 2, and then add these two scaled vectors to get the final vector. As you can see, that's the black dashed line. It overlaps with the green dotted line that we had earlier. So again, these rules hold. The another example here is if we try and rotate. So if we have this set of vectors, the blue and the red, as we see x1 x2, and we try to add them first and then sort of rotate it. I'm trying to show rotation by simply negating the value, and then it is the same thing as negating those values first and then summing them together to get the same vector that we had earlier. And finally, for scaling, as we looked at, if we have a vector x, as we see here, if we scale it, that is multiplied by scalar, in this case a is equal to 2, we get the new vector x2, which is twice as long. And then we so that's what we get. And let's say we flip it to by multiplying it by -1, we get this vector. Now this is the same thing as multiplying x1 by -1 first to get that vector shown here by black arrow, then scaling it by multiplying it by 2, which gets us this dotted arrow, which overlaps the green dotted arrow that we had earlier. So these are these are the sort of visual explanation for the rules for linear transformation that we looked at here. In the next video, we'll build on this and look at a couple more in-depth examples.